Okay, hi everyone. So let's talk about oblique asymptotes for rational functions. So earlier we talked about we have vertical asymptotes for rational functions, we have horizontal asymptotes for rational functions, but now we also have oblique asymptotes. Oblique asymptotes, oblique meaning like it's diagonal. Right? So this could be a line basically. So let's go ahead and let's give its conditions and write out what it's about. So if you have f of x is equal to a of x over b of x, where a of x and b of x are both polynomials. Alright, so a of x, let's also write our conditions. These are both polynomials. Right? But they have with no common factors. With no common factors. This is also very important. Right? Meaning that you can't cancel anything out from the top and bottom. And b of x does not equal to 0. So we can't have our denominator obviously equal to 0. Then there exists an asymptote. So f of x is the whole polynomial, like the whole expression, the whole rational function. It has an oblique asymptote. Where especially if the degree of the if the degree of the numerator minus the degree of the denominator is equal to 1. Alright, so these are our conditions. There are polynomials with no common factors, and especially if we take the degree of a of x, the first polynomial, our numerator polynomial, and then minus the degree of the second polynomial, b of x, and if that equals 1, then we definitely have an oblique asymptote. So let's look at an example so you can also see what I'm talking about. So let's say we have x to the power 4 plus 3x cubed over x cubed minus 1. Alright, and all of this is the f of x that we're talking about. So essentially this first part is our a of x, and then this bottom part is our b of x. This is an equal sign. Okay, so let's go ahead and try to factor it down and see if there's anything else that can be canceled from here. Well, for the top part, I can take out an x cubed, leaving me with x plus 3. For the bottom one, I have perfect cube, the difference of perfect cubes. So it's going to be, because x is a cube, is x cubed, obviously, and then 1 is also a cube. We can cube that. So we have x minus 1, apply the difference of perfect cubes. Then we have x squared plus 2x plus 1 in the bottom. See, we have no common factors. X plus 3 can't be canceled with anything in the bottom, neither can the x cubed. And say likewise with the denominator, x minus 1, x squared plus 2x plus 1, we can't cancel anything out. So we already said that they have no common factors, and of course b of x cannot equal to 0. That's by default, okay? Next thing is, now let's check the degrees. We need to check if the degree of a of x minus b of x is going to equal 1. Alright, so the degree of a of x, alright, if we look at the highest one, it's right here. This is our degree of a of x. So our degree is 4, and then the degree of our second one, b of x, is 3. Okay, and then obviously, the degree of a of x, we get 4 minus 3 is equal to 1. So this is the degrees. Alright, and this also checks out with what we have here. We see that it is also equal to 1. So this f of x has an oblique asymptote. Now we need to figure out what that oblique asymptote is. So at the end of the day, the oblique asymptote is going to equal a of x divided by b of x. Okay, let's also go ahead and write that down. So at the end of the day, we satisfy all the conditions. Our oblique asymptote is equal to a of x divided by b of x with no remainders. So we have to have no remainders as well. And so let me show you what this is. So let's go back to our example, a of x divided by b of x. So our a of x was x to the power 4 plus 3x cubed, and then we have x cubed minus 1. Okay, so just to give us some space, I'll scooch this down. And let's continue working. Alright, so we want a of x, so our oblique asymptote is a of x divided by b of x, and in our instance, that is x to the power 4 plus 3x cubed divided by x cubed minus 1. So I guess at this point you can imagine what we're going to use. Long division. Yes, exactly it. Alright, so let's use our long division skills. X to the power 4 plus 3x cubed. All of that divided by x cubed minus 1. So using our long division skills, alright, x times x cubed, that's going to get us x to the power 4. So you kind of move it over one slot. Okay, so it's going to be, what do we get? We get x times x cubed minus 1 is x to the power of 4 minus x. Okay, and then we get, let's see, power 4 minus, these cancel out, so we're left with what? Plus 3x cubed minus x. Okay, so this is our, actually plus x. Alright, that's our answer. We don't need to put a plus in front of the 3x cubed. So 3x cubed minus x, so that's 3x cubed plus x. That's our final answer. Next thing we do is we'll see that we need to multiply our, we'll take it times 3, x cubed minus 1 times 3, then we can get this value here. Because your goal in long division is to try to get this first value, 3x cubed. So if I multiply what I have outside here, x cubed minus 1 to 3, what is it? It's going to be plus 3. Right, I will get 3x cubed minus, so we get what? X and then minus 3. Okay, so it's minus, subtract, these go away, and then x minus 3, that we're left with what? X plus 3. Okay, so now we're starting to get some remainders at this point, but the key word here, oblique asymptote, it said with no remainders. So if you get a remainder, then at this point you just kind of forget about it actually. You don't need to worry about it anymore. And then you just take this value right here, and that is going to be your oblique asymptote. So we have an oblique asymptote for this function at y equals x plus 3. Alright, and then this would be our final answer if the question were, what's the oblique? But real quick, before you go, I actually have a graph of y equals x to the power 4 plus 3x cubed over x cubed minus 1. Okay, so this is the problem that we were working on, and this is its graph. Okay, now the oblique asymptote that we found is y equals x plus 3 right here. So I will go ahead and click that. And now if you look, oh, here it is, the oblique asymptote.